These are the frequently asked questions for pre-calculus for section 3.2 day 2, the second day, the ones that I had not answered already on the other video. So it says, determine the atmospheric pressure outside an aircraft flying at 52,800 feet, which is 10 miles above sea level. And I want to make sure that I'm using the miles above sea level because we have to go back and get the formula that we had in our notes that we derived based on the information we had for atmospheric pressure at that time, and that is the formula that you see right here, and that's right in your notes. So all we have to do is put in 10 miles for the height, and we have this thing. So we want P of 10, which is 14.7 times 0.5 to the 10 divided by 3.6 power. And when we punch that in, we will get 2.143, and that's the atmospheric pressure, so that's pounds per square inch. And that's all we need to determine the atmospheric pressure outside an aircraft flying at 10 miles above sea level, 2.143 pounds per square inch. And that's because our formula was already built for miles above sea level. Then, the next one up is number 43. And this one says, use the 1950 to 2000 data in table 3.12 and exponential regression to predict Los Angeles population for 2007. Compare the result with the listed value for 2007. So here's what we're going to do. It says let 1900 be t equals 0. So it would be 50, 60, 70, 80, 90, 100. And then we're not going to put that one in, and here's why. Your book seems to be leaving that information out when they want to ask us about those individual dates. So we'll go ahead and get that into the calculator. And I had decided when I put it in, I didn't want to mess with the thousands. I wanted everything to be right there. So stats, edit, to show you. I went ahead and put those in thousands already. So it is stored in there that way instead of punching it in as the 4 numbers they gave me. So stats, calculate, and for this one we are supposed to do our exponential regression, and that is going to be down here. And that is our 0. And we'll press enter through all of these and have it calculate. And there it is. So our model for this regression, we'll use P of t for Los Angeles, is going to be 1149619.043 times 1.012 to the, oops, better use t up there, like so. And then it says, okay, now go ahead and use your model, figure out what you would get for 2007, which would be taking 107 and putting it up in here for t. So it would be 114961.043 times 1.012 to the 107th power. So when we get that all in and we take a look at P of 107, we see that that is 4119730.313. Well, this is about people, so 4119730 people is what we would round to. 4,119,730. And really, even without the zeros, if you didn't punch those zeros in, that's still what you're going to get anyway. You're just going to have to add the 3 zeros in at the end because the table said this was in thousands. So what they want us to do is compare that with 3834000 people. This is from the table. Well, to compare means we need to see the difference. So we'd go ahead and take our answer and we would subtract 3, 8, 3, 4, 3 zeros, and that gives us 285,730 people. So you can see that we're a little too high, you know, so that's how we would compare it. We would say that our result was higher by that 285,730 people. And that's how we compared the results. Again, you might have had a little bit different answer if you kept that 2007 and you put that into your stats when you got started and did 107, 38, 34. Either one of those is going to be close. That's what this is. This is about predictions. So the book chooses to leave that one off when they put it in, and that's why you're going to see their numbers might be slightly different than your numbers. For number 47, I'm going to have to enter these into the table and then get back. And this is a problem we had previously done. I believe it's just exponential growth. And this example says we're using all of the data in table 3.9, but we're going to compute a logistic regression model and use it to predict the U.S. population in 2010. So I already went ahead and put the data in. This one, because it was in millions, and again, you can see all of that just by looking at the table. You can find the label that they have, and this one is in millions. And I'm not going to put in all those zeros. You know, we should get a good enough look at it with the millions in there. And logistic regression, stats, calculate. And again, we're going a ways down. If you remember, that is capital letter B. The shortcut would be to go ahead and hit the letter B. And to do that, you have to use those alpha keys to get that piece in there. So that's the one I need. Enter. And I do have it in list 1 and list 2, so I'm going to go down to calculate, hit all of that. That's going to take it a little bit. Generally with the color calculators, it takes it a little bit longer to do the logistics and to do the graphing that we need for that. So there it is. And we write it down. This was population, so I will do P of T according to time. And our C value here is 299, but then a 6 to round up would be 300. And that's going to be over 1 plus our A value 9.318. There we go. Final is using the E value, so we will have plus 9.318 E to the negative BX. So negative 0. Well, we have basically 16 thousandths with our rounding there. And our power, which I was going to use T for instead of X there. So using all the data in table 3.9, compute a logistic regression model. Use it to predict the U.S. population in 2010. Well, this started in 1900. So we would go ahead and say, all right, well, we'll do some subtraction here and figure out how many years this is going to take. From 1900 to 2000 would be 100, and then we went to 210, so we've got 110. That means we need to put 110 in here. If we save it, which we could do, you know, why don't I show you how to do that? Let's do stats, calculate, and then we needed that B. There we go. All right, the button got stuck there, so I've got that fixed. I'm going to go ahead and store this in the Y variable. So variables, number 1, you have to arrow over to Y variables, and number 1 again, and then have it calculated.
Elena Swanson to the
Once we do this, when we hit the enter, what it's going to do is give us that logistics again, but now it has stored that in our y sub 1. And what that does is that allows us to just look at the table for whatever year that we want. And since we wanted it at 110, I'm going to go ahead and hit second table set, and I'm going to have the table start at 110. And that way, if I hit second table, I can get my y value for 110 is 310.57, and then I can just put the zeros on for the millions. Now I wanted to show you that piece, but this isn't going to be as accurate as if we actually put the 110 in ourselves, because notice that they're only going to 2 decimal places here for this y sub 1 value. But if we hit y sub 1 and actually highlight that, then we can see all the decimals that we would have there. So that's what we want to do. We want to see that y sub 1 piece. So it is really, well, it's really nice because you don't have to go through all the punching in and, hey, did I get parentheses around my denominator and all that good stuff. So P of 110, we have 310.573805,067. Now, why did I put all that in there? Because, reminder, this was in millions. And if it's in millions, we're going to need to move this over 6 decimal places. 1, 2, 3, 4, 5, 6. So we would have 310.573805.069. And then we would make sense of what that means for what we're doing. And what that means for us is population. So we want to round this to the nearest person, which it already is. We would not have any rounding in this one. And we have 310,573,805 for our prediction for the year 2010. 50 is the next one on the list. And this one has us using the data in Table 3.14 to compute a logistic regression model for Arizona's population for 2 years since 1800. And then based on that model and the New York population model that is in this exercise right here, 56, will the population of Arizona ever surpass that of New York? If so, when? Well, the pretty obvious information that we have here is that for New York, that limit is 19.875. And if we read this, we note that this was started in 1800, just as this example is, and the population is in millions, just as this example is. So really what we're supposed to do is churn out that logistic equation and then take a look at that maximum sustainable limit that we see up there. So I had stopped the recording so I could enter all that fabulous stuff in, and now we will do stats. Oh, probably should see here that since this was since 1800, make sure that you have the corresponding numbers for the years 1900 to 2000, which would actually include some 100s here and then a 200 for that last one of 2000, which 2000 minus 1800 is 200. So stats, calculate, and we know that this one is under B, and I'm going to go ahead and do the shortcut for that and hit alpha, and then apps, because that brings it to B. And we can see up at the top that that's logistics. Since this calculator is giving me a lot of trouble with the up and down arrows, I'm just going to go ahead and do the shortcuts. And I'm just going to go down to calculate, since they're not asking us to give them any information about any years. And again, this sometimes takes the calculator a little while to give us that logistics. So while it's going, you can think, okay, really, all I'm doing here is I'm taking a look at the C value, the value up at the top. But they did want us to write the whole model. So when we look at the model that they had from the other example, we see that they did use a model that was based with E. So we'll be able to just compare this directly. So when our formula is going to be C over 1 plus A times E to the negative bx, which of course fits the model they have for number 56. our model will be y equals 15.642 with rounding over 1 plus 11799.360 times e to the negative, and I'm going to put out a space with that arrow in the way there, negative 0.043x for our power. So there's our power of e there. But again, what we are looking at is this. And for Arizona, we have 15.642 million for the population. And for New York, that maximum sustainable population is 19.875. So we would write something along these lines, 6 decimal places for the zeros there is going to be greater than, and we're going to do the same thing for 15.642. We need 6 decimal places, 15.642,000, because that shows we know what we're talking about. You know, they're both in millions, and 19 million and change, almost 20 million, is definitely greater than almost 16 million. So will the population of Arizona ever surpass that of New York? No, none. It isn't going to. It just won't happen. And the next one up on the list is 55. This one didn't require me to punch anything in for the table, so it says we have a single cell amoeba that doubles every 4 days. All right? So amoeba, single cell amoeba, I don't know, maybe I'll use A for amoeba and T for time in this one. And it's a single cell amoeba, so there's one cell, but it's doubling, and it's doing that every 4 days. So if I have T stand for number of days, I'm going to need T over 4 in order to make this work. And you could certainly use D for days, whatever you want to do here. And then it says, when is this going to produce 1,000? So when is 1 times 2 to the T over 4, when is that going to be equal to 1,000? Well, the first thing I'm going to do here is I'm going to use logarithms this time. That graphing calculator that I have there is not exactly a fabulous thing to work with. So when I get to this point, I'm going to go ahead and take the natural logarithm of both sides, and that'll give me the natural log of 1,000 equals, and in this case we have the natural log of 2, but this is a power. And remember from the properties of exponents that powers are multiplication. So I'm going to bring that in front to be multiplied by that natural log of 2. And then we'll go ahead and divide both sides by the natural log of 2. And again, why are we using natural log? Because in calculus, natural log makes a lot of your math easier. So now we have natural log of 1,000 over natural log of 2 equals T over 4. And we would go ahead and multiply both sides by 4. And that will give us T. Now if you're going to punch this in all at one time, you need to use parentheses there so the calculator knows I'm going to do everything on the top, and then I'll do everything on the bottom and see what we get. So let's go back over here and let's punch this in and see what we have. So main screen here, and we had 4. I usually punch it in separately, but just to show you here, I'll use parentheses. 4 times the natural log of 1,000 and double parentheses at the end, divided by, and then we have the natural log of 2. Now for that I didn't need an extra set of parentheses because that's all we have. There isn't anything being added, subtracted, or raised to a power after that. So we get this, and then we would go ahead and round it. We've got 39.863 days. So we could certainly round that to about 40, and this one just happened to be multiple choice, and 40 is one of those choices. Get back up here. Problem. And that is D. It is approximately 40. Number 58, I am going to have to enter some data in. I have all the data in for this one, so now it's time to do the number crunching. And this says use all of the data in tables 3.9 and 3.15. And first A, based on exponential growth models, will Mexico's population surpass that of the United States, and if so, when? So what I did was I went ahead and put the US data in for list 1 and list 2, and I put the Mexico data in for list 3 and list 4. We could not just use the X's as L sub 1 this time, and that's because of the population data. We did not have exact matches for that population data, so our X values were going to be different. So let's see what we get for exponential growth. So stats, calculate, and our exponential growth model was 0, and we could see its exponential regression up there. And the United States will be list 1 and list 2. And I am going to store this because we want to see later when are they equal to each other. So we're going to put this under variables, y variables, number 1, number 1. And then we're going to let it calculate. So it's doing that exponential regression, and it's showing us that model right now. And certainly on your homework, it would be great if I could see you write that model down. Y equals 81.041 times 1.013 to the x. Something along those lines, probably maybe p of t, p of x, whatever you want to do for that. Well, there was the United States. Oh yeah, that was the United States. Now we're going to do Mexico. So stats, calculate, and we're back to exponential regression, which was 0. But this time I have to make sure that it uses list 3 and list 4. So second, list 3 for my x's, and then second, number 4, list 4. And I'm going to store this in y sub 2. So variables, y variables, number 1, but then number 2. And enter, and enter. So all of that good information is sitting in my y equals window. And if I set my window reasonably, then this ought to work. Whoops, not that one. There we go, window. So years is what we're looking at. And if we take a look at those two tables and we try to figure out when this is going to happen, we realize, it might take a couple of 100 years here. So I'm going to put a 200 there in the hopes that we can see where they meet. And then what they asked us to find in this problem was when will it surpass that of the United States. So we take a look at those populations, and we see that we were already at 154 million. Maybe I'll try 300 million. Might be too much, but that's okay. We'll still see the intersection. So there's the United States. That was the first one that I had graphed. There is Mexico. So what do we see? They're not intersecting just yet. So let's go into the window. They were not intersecting with the window that we saw. So I did some tweaking here in the window. And if we go from 0 to 400 for the number of years, and the Y max gets increased huge, we're talking about 10,000 million here, then when we graph, we can see an intersection. So second trace, number 5, enter 3 times. And we're talking about approximately 338 years later. So we'd have to remember, okay, let's see, we started this thing in 1900, and we're saying this is going to happen approximately 338 years later. So sometime during 2238. And that's about as exact as we're going to be able to be on that. Remember, this is extrapolation. We're trying to make a prediction about data that are well outside of the window that we're looking at. So we've got part A done. Based on exponential growth models, will Mexico's population surpass that of the United States, and if so, when? And we've got it around 2,238, sometime during that year. But that's, again, with extrapolation, you never know. Things could change quite a bit. So we just have to say, hey, we think that's when this is going to happen. B says, based on logistic growth models, will Mexico's population surpass that of the United States? And if so, when? Well, we have to go back and do logistical regression. So let's see what we get here. All the data is still in there. Second, quit, and then we would have stats, calculate, and remember logistical regression is that capital letter B. So alpha, apps. And I'm going to go ahead and do the United States first again. So I'm going to do second, list 1, second, list 2. And I am going to store that because if they do intersect, we want to see that. So variables, Y variables, number 1, and enter and enter. And again, logistical formulas will take a little bit longer, so it might be a little bit here. But this will be the United States model. And what we want to pay close attention to is that C value. Because that C value is going to give us that sustainable limit up there, that maximum sustainable limit. So for the U.S. we have 809, well, 0.300 if we round. And let's see what it is for Mexico. Again, I am going to store it just in case. So stats, calculate, and that is going to be our B, so alpha, apps, logistical regression, but now I need list 3 and list 4. Because that's where I put that data in. I wanted that all in at one time so that we could go ahead and do all of this math. So variables, Y variables, 1, but now number 2 for Y sub 2. Again, this is just in case the Mexico sustainable population ends up being higher than the United States. Again, takes a little bit for the calculators to get us all of that good math. And we see that for Mexico, that maximum sustainable limit is 165.379. So we found our answer. We're never going to see the Mexico population surpassing that final amount up there. So for B, based on the models, will Mexico's growth surpass that of the United States? And if so, when? We would just put no, never. And then these pieces of information that I have are definitely explaining why not, And in fact, when we've done that, as you read C, it says, what are the maximum sustainable populations for the two countries? So we're going to go ahead and use that information and say, all right, well, this was in millions, so 809, and then it's just a matter of how many decimals that you want to put in there. So 809,300,123, if we want to go ahead and get all of those millions back in there. And then for Mexico, 165,379,000, and that's going to be millions for Mexico. Now, if this is on the AP exam, we probably want to go back and get into Y equals so that we can see exactly what it was and really impress them with moving those decimals over and talking about those millions, just coming up here and saying, all right, well, there's 3 decimal places, there's another 3. So 809,299,600 and looks like approximately 7 million people. And then for Mexico, do the same thing. those 6 decimal places and say 165,379,407, so that we have all of those decimals in there. But you're going to notice that your book for the answers in the back, it must have really been scrunched for type space, because they just stopped at 809 million and 165 million. So even with the answer I have up there, a little more specific than what they had. And then D says writing to learn. Which model, exponential or logistic, is more valid in this case, and justify your choice? Well, of course, this is going to be the logistic growth, and that's because there is a limit to the sustainable population of a country. So for D, it will be the logistic model, because population does have a maximum sustainable limit. So that was number 58, and I think I managed to get them all.